Alright, so here's what we're going to learn today. Today is going to be a long video, and even though it's going to be a long video, I still left things out. So after this video, when we come to class, I will still have to explain a couple more things, but I really did not want to overwhelm you, and there was a lot of content today. So anyway, let's get started. The first thing we're going to talk about is something called the heating effect of conductors. And this is something that you probably have experienced, which is that when you have a battery, so here's your battery, that's a pretty bad battery, and then you put a wire between the two sides and you leave it for a while, the wire gets hot, so this thing starts getting hotter and hotter and hotter. Why does this happen? Well, the reason this happens is that inside the metal, the atoms are arranged a little bit like this, like in a crystal, and we call this arrangement a lattice. And the electrons, the outer electrons of these atoms, are actually free to move all around the conductors. They just can go around. This means that from time to time, they will impact one of the atoms in the lattice, and this will be an inelastic collision. And in an inelastic collision, remember that what happens is that energy is not conserved, which means that the energy that this electron has is going to end up spread through the lattice. This means that these atoms are going to start to vibrate more, and macroscopically this translates in a heating of the circuit element. So this means that because of these constant impacts of electrons on lattice atoms, then we've got a heating effect. And why are the electrons moving? Well, they're moving because between the two sides of the battery there's a potential difference. And remember that when there's a potential difference, an electric field has to appear also. And it's this electric field that pushes the electrons to move all around. And the electric field is immediately established across the whole conductor. That's why even though the electron speed is really, really slow, it doesn't mean that the electrons are coming from here. All the electrons of all the cable are all moving this way because of this electric field that has just been established all across the cable because of the potential difference between the two sides of the battery. Now, the next thing that we need to discuss is the notion of resistance. Every single conductor, because of what I just told you, does present a resistance to the flow of current. So the current tries to flow through, but it can't. Or well, it can, but it just does so slower than it should because of all these continuous collisions here. So even though most conductors have very little resistance, and that's why we say it's zero for all practical purposes, all conductors have some resistance. The only thing that does not have any resistance is something called a superconductor that we're not going to get into. So there are some conductors where this resistance cannot be ignored anymore, and we call them resistors. And these resistors, the number that describes them is called resistance, and we express it with an R. Now, what I will try to do is try to derive a law that relates resistance to voltage and current, and you have already done this in the IGCSE. So here's the idea. Imagine that I have a circuit, and hopefully from the IGCSE you remember that this is a potential difference, and here I have a wire, and here I have a resistor with resistance R. And then I ask myself, okay, so how much current will I get through here? And then I think, well, if I have lots of voltage, then I'll have lots of current, because the more the voltage, the more electric field here, therefore the more the electrons are being pushed around. Therefore, current has to be proportional to the voltage, so this has to be multiplying. Now what about the resistance? Well, if I have lots of resistance, I'm going to get less current because it's harder to get through. Therefore the resistance has to be dividing. I'm going to put this dividing. I can rearrange this equation now and put it like this. R equals V over I. And this is actually the definition of resistance. This tells me that if I want to know the resistance of something, I need to measure the potential difference between these two sides, and then I need to measure the current that's going through the resistor, and then the ratio of these two things will give me the resistance. So this is, again, this is the definition of resistance. It's not something that you derive, that's just how you define resistance. Now, what are the units of resistance? Well, that's easy to determine. All we need to do is to take a look at the units of volts and current, right? So we have the units of resistance. Remember, this means units have to be the units of voltage, divided by the units of current, which is, as everybody knows, volts divided by ampere, and we call this ohm, which is this little weird symbol, which is a Greek omega. So that those have to be the units of resistance. Now, in some cases, this resistance stays constant, no matter what the voltage between these two things. So, if I had to draw a voltage current graph, what I would find was that as I increase the voltage, the current increases always at the same rate, so that the resistance is constant. This does not always happen. Sometimes resistances depend on the voltage, and then as I make the voltage higher, then the intensity gets higher, or sorry, the current gets higher, or it gets lower. So we get things like that. Actually, I should draw really a current voltage graph. So for example, as I make the voltage higher, I could get something like this. Or I could get something like this. And many other things. So when these things happen, we say that our resistor does not follow Ohm's law. So let me just rephrase this. The basic idea is that if a resistor follows this law, that is, resistance is constant, then the current will be proportional to the voltage. And this is Ohm's law. So Ohm's law says that the current is proportional to the voltage. But again, only some resistors follow Ohm's law, and we call this ohmic resistors, as in following Ohm's law. And some of them do not follow Ohm's law, and this is not a straight line, and then we call them non-ohmic resistor. So this would be a non-ohmic resistor. Because, as you can see, the current is not proportional to the voltage. That's it. Now, I will do this very briefly because we did this in the IGCSE already. The idea is that if I have a wire like this that has a certain area A and a certain length L, the resistance of the wire depends on both the area of the wire and the length of the wire. So, and it also depends on some characteristic of the metal that we call resistivity. It tells us how resistant that particular material is. So this little Greek letter, rho, is the resistivity. And we want to know how resistance depends on these three things. So let's just think about this. So resistance equals, now if the area is very big, then there's way more space for the electrons to go through. Therefore the resistance should go up or down. Pause the video and tell me. Okay, hopefully you said down, because again it's easier for the things to go through. Therefore this should be inversely proportional to the area. So the area should go here. However, if the length is really big, then I should have more resistance because the electrons have to travel more resistor, so then it's harder to get out. So the more length, the more resistance. And finally, this basically tells us how resistant the material is. So the higher the resistivity, of course, the higher the resistance. So this goes something like this. I will leave it as an exercise for you to figure out the units of resistivity. Now, we've seen before that the work done by an electric field is the potential times the charge. That's just the definition of potential, remember? Now, we also know that the power that an engine delivers is the work per unit time. And what we can do is combine these two equations to find the power dissipated by a resistance. And you would ask yourself, why would a resistance dissipate power? Well, simply because of what I told you of the lattice electrons. When we have something like this, there's electrons here in the lattice, there's nuclei in the lattice, and then when the electrons bump into these nuclei, they lose energy, and therefore this energy is released as heat. The energy that they release every second, that's the power dissipated by that resistor. So now let's calculate how much power a resistor will dissipate. Well, I will start with this equation. So power is the work per unit time. and the work done by the voltage is just V times Q. But instead of writing Q, I'm just going to write increment on Q as the little charge that's going through there at that time. So I'm just going to write V times increment of Q divided by increment of time, and you may remember that this is nothing but the current. So power equals V times the current. Ta-da! And that's how we derive the equation that tells us the power dissipated by a circuit element. We just need to know the potential difference between the two sides, the current going through it, and then we know the power that's dissipating. Now sometimes we find other ways of expressing this that are more handy for whatever situation that we're using. So sometimes we will know the current and the resistance, sometimes we will know the voltage and the resistance. So we will want to rewrite this in ways that will help us later on. Now this is extremely easy to do. All we need to do is to use this equation that V equals IR. So if we use this equation, instead of V I can write IR. So I get that power equals IR times I, and that's of course I square R. And then we can also rearrange this thing here to express I in terms of V, right? So we can write I equals V over R, and then I go back to here and I replace I by V over R. So I do the same thing, and you should be able to do this yourself. So V over R times V, and that's V squared over R. And these are the two equations that will give us the power dissipated by a resistor. Well, the three. 1, 2, and 3. And you can use any you want depending on the situations that you're in. Now, for reasons not entirely clear to me, I have to go into the distinction between EMF and voltage. And EMF, we did that last year, and it stands for electromotive force. So electromotive. And this is really a bad name because this is not a force at all. Now, this is how we define EMF. Imagine that I have a battery here, and this battery is pushing its charge to go around, right? So it's doing this. It's giving energy to every charge that goes through. Well, EMF is just the work per unit charge that this battery does in order to push the charges out of it. So EMF is just defined as the work per unit charge that the battery does. And you'll say, like, well, wasn't that the potential difference, the work per unit charge? Yes, it was. So then what's the difference? Well, the difference is that normally batteries have a small resistance in them. So this really doesn't look like this, but it looks like that. There's a battery plus a tiny little resistance. And this tiny little resistance dissipates power, and because of this the battery gets hot. So that's why when we are using a battery for a long time, the battery gets hot. Which means that actually the potential difference that we get between the two sides of the battery, which would be between here and here, is actually less than the EMF of the battery, because some of the energy that it's giving the electrons is lost. So then we distinguish between EMF and voltage, saying that, well, EMF is the energy that this battery gives every single electron that goes through, every single charge, but the voltage is really the one that we really get to do useful stuff. And because there's this little resistance here, we actually get less than we're being advertised, because some of the energy is lost here. That's all we need to understand. Now, again, we did this last year, so I'm going to run through this. Remember that we can put resistors in series, and in series just means one after the other. 1, 2, 3, as many as we want, right? So if I put resistors in series like this, what's the total resistance? Well, the total resistance will be this, plus this, plus this. And this is just common sense. And you can actually deduce this, and I actually encourage you to deduce this as an exercise, using the fact that the potential difference also adds up. So the potential difference between here and here is equal to the potential difference between here and here, plus the potential difference between here and here, and then the potential difference between here and here. Now, what if they're in parallel? I'm just going to do this with two of those. Well, if we're in parallel, all we need to use is two facts. The first fact is that because this is a conductor, all parts of a conductor are at the same potential. Remember that from the IGCSE? The basic idea is because electrons can freely move in here and freely move in here, then obviously there can't be any difference between the potential in these places, or at least the difference is negligible. So this means that the potential difference V between here and here is the same as the potential difference V between here and here. Okay. Now the next thing that we need to realize is that if we have a certain current I coming here, it will spread out into I1 plus I2, right? So then we have that I, the total current, will be I1 plus I2. One goes to R1, the other one goes to R2. And the idea is that we want to find the equivalent resistance. So we want another circuit that looks exactly the same, but instead of two resistance, it has one, right? So what we're saying is that these two resistances are equivalent to another resistance that has a value that we're trying to find. Okay, so here's what I'm going to do. I'm going to take this equation here, and I'm going to express this in terms of this, and this in terms of this. So first thing, I. So the first current. Well, this current will be V over the total resistance. So let's just write that down. So V over the total resistance will be equal to, now I1 is going to be V over the first resistance, right? Because current is V over R. So V over R1. And of course, by the same reasoning, I2 is going to be V over R2. So V over R2. And then lo and behold, we can get rid of these V's, and then we get the famous parallel resistance equation, which is 1 over total R equals 1 over R1 plus 1 over R2. And we did this in the IGCSE, so again, there's no need to go too much into this. Okay, so what if instead of the typical circuit we have something like this? So here's a resistance, here's another resistance, here's a resistance, and then we have this, and then we have this. Now you can see that this would be a nightmare to solve because we have two sources of potential, and then we have all these resistances. We don't know if they're in parallel, we don't know if they're in series. This is a nightmare. Who would do this to us? Well, I'm doing this to you. It turns out that to solve this, we need this thing called Kirchhoff's laws, and this is a little bit complicated, but it's the only way to solve this kind of circuit. And this was not on the syllabus last year, but now it's on the syllabus, and we need to learn it. So, tough luck. I learned this in college, by the way. So, the basic idea is that there's two laws. One law refers to potential, and one law refers to current. And both laws are actually quite commonsensical. So imagine that I want to know the current going through each branch of this circuit. How would I do it? Well, the first thing that I need to realize is that if I take a loop of current, of wire, so here, right, this is a loop of wire, this is another loop of wire, this is another loop of wire, anything that goes back to itself is a loop of wire, and I start adding up potential differences, I'm going to get zero. Why? Well, because, okay, this one decreases the potential difference, this one decreases the potential difference, this one decreases, and then this one increases. So that by the time I'm done with the loop, I get zero potential difference. What I'm saying is that if a charge went all around the loop and then back through the battery and then back here, it would have the same energy that I had when I left the battery, which makes sense, right? The only thing we need to take into account, and this is a matter of notation, it really doesn't matter. We are going to take the potential difference in the resistances to be negative, in the sense that the energy of this guy is decreasing, right? This is like as if it was a waterfall. Every time that I go through a resistance, I fall a little more, fall a little more, fall a little more, have less and less, and this is like a pump, brings me back up. So I'm going to take the potential difference here to be negative in the sense that this is falling, and then here I'm going to take the potential difference to be positive. Okay, so for example, this could be 6 volts, and then this could be minus 2 volts, minus 2 volts, minus 2 volts. And Kirchhoff's law tells me that if I add up all these potential differences, I will get 0. So 6 minus 2 minus 2 minus 2, that's 0. Good. So basically that if I add all potential differences in a loop, I get 0. Let's write that down. Ta-da! See, it just appeared magically. Wow. Okay. Now, the second law relates to current, and that's even more obvious than the first one. All that it says is that the current that goes in has to be equal to the current that goes out. So, for example, if here I have a current I1 going in, then this is I2, this is I3, so I1 has to be equal to I2 plus I3. And that's it. So the basic idea is incoming current equals outgoing current, period. It could be that these two are incoming and this one is outgoing. It could be that this one is incoming, these two are outgoing. It doesn't matter how you choose things, this is always going to happen. And if you choose things wrongly, all that's going to happen is that one of these guys are going to pick up a negative sign. So they're going to say, no, no, you thought it was going this way, but it's actually going this way. And that's it. By applying these two laws, the PD law and the current law, you can solve any circuit. And I know it's actually a little hard, and I will give you a demonstration when we're in class. Wow, a creepy cat. So yeah, I was bored, and you know, this has been going on for a while, so here's a creepy cat to entertain you. I'm running out of cats, so I'm gonna have to choose a different animal for the next day. Anyway, so now comes the easiest part, which is just to talk about ammeters and voltmeters, which is how we measure current and voltage. And the idea here is very simple, and this is not going to take a second. So let's just get rid of the creepy cat. Okay, so imagine that I want to measure the PD across this resistance. Well, if I want to measure the PD across this resistance here, what I need to do is connect something between here and here, right? Because if I just connect it here, there's no difference. And it needs to be a difference, so I need the two sides, right? So I need to connect something here. And what I connect is something called a voltmeter. But the problem is that if this voltmeter had a low resistance, then current would start going through the voltmeter and not through this resistance, right? And because then the current would be lower, remember that V equals IR, then I would measure a lower potential than I would be measuring, because the current here would be lower than it's supposed to be, therefore the potential here between these 2 points would be lower than it's supposed to be. So then I have a problem. How do I make sure that this does not decrease? And the only way to make sure that this does not decrease is for the resistance of the voltmeter to be very, very big. Now in an ideal voltmeter, the resistance is infinite, which means that there is no current going through here, so that this potential difference stays exactly the same. This is an ideal voltmeter. However, in reality, what happens is that voltmeters do have a resistance that's non-negligible, very large but non-negligible, so they measure this V that's a little bit lower than it should be, because the current is a little bit lower than it should be, because some of it goes to the voltmeter. And that's all we need to understand. Now, what if we want to measure current? So again, let me get rid of this. Let me show you the creepy cat again. And now, so here's my resistance, and I want to measure current. Now, if I want to measure current, I really need something right here in the middle of things, right? Because I need to see how much current is going through it. So it needs to go through here. Now, if this is V and this is R, we know that the current is V over R. But what if this thing has a resistance? Then we need to add it here, right? So then it will be V over R plus little r of the ammeter. So what happens is that just by putting an ammeter here, I am getting a smaller current reading than I should be getting, because this has an internal resistance. So what is the only way to avoid modifying our measurement? Well, the only way is to have the resistance of this ammeter to be 0. If this is 0, then this goes, and then we get the real current measurement that we were getting before. Therefore, an ideal ammeter has 0 resistance. In practice, though, we get a smaller current that we should be getting, because this has non-negligible resistance. That's it. Alright, so we're done. Let's see if we went over the learning objectives. First, draw circuit diagrams. Yes, we did that. State Kirchhoff's circuit laws. Yes, we defined resistance. We stated Ohm's laws. We defined resistivity. And we identify ohmic and non-ohmic conductors. Remember, the ones that go like this are non-ohmic. The ones that go like this are ohmic. Solve problems, that's what you're going to do. Calculate combinations of resistors in parallel and series circuits. Yes, you're going to do that. And describe ideal and non-ideal ammeters and voltmeters. We just did that. Now, I purposefully left a lot of stuff out today. So I left a lot about cells out, and I left a little bit of practice for Kirchhoff circuit laws out. And that's what I'm going to start with in class. So I'm going to spend the first half an hour going over some extra theory, but I really did not want to make your heads explode today with this video. Alright guys, so I'll see you in class and have fun.